Hello viewers, in this video I will discuss about the value of entropy for various processes like isothermal, adiabatic process, isochoric process, isoboric process, and also we will see the general equation for a gas. Okay, so what is the general or how will you express the change of entropy for a gas not under particular conditions. Okay, so let us take a gas. Let us take a gas. So let us see that it moves from state 1 to state 2 under some conditions. Okay, so let us take the value at state 1 as, so the condition of state 1 as P1, V1 and T1, and it 2 as P2, V2 and T2. So it moves from state 1 to state 2. Now we have to find the change of entropy when it moves from this state conditions. Okay, for that we will take the first law of thermodynamics equation. So let us take the delta Q is equal to delta U plus delta W. Okay, so this is the first law of thermodynamics equation. You all know that. So delta Q is equal to delta U plus delta W. Let us take this. Some heat is supplied and work is done. So let us imagine like that. Okay, some heat is supplied and some work is done. So we can write delta Q here. The value of entropy, the heat content of the internal energy could be written as mu here. See, this mu is nothing but number of moles, that is the amount of substance. Okay, so mu Cv delta T. So Cv you know it as molar specific heat capacity. So specific heat capacity. Okay, so you know that Cv is molar specific heat capacity. So mu Cv delta T plus work done P into delta V. So here we take it as positive work. Okay, P into delta V. This is delta Q. Okay, so now I'm going to divide both sides of the equations by T. So I'm going to divide both sides by T. So delta Q by T, which is equal to mu Cv delta T by T plus P in delta V by T. Okay, so now, so you know that this change of entropy delta S as delta Q by T, where the temperature remains constant. We have another equation, delta S is equal to integral of delta Q by T, where the temperature varies. So in most of the conditions we will take only this equation. Okay, so this delta Q by T can be written as ds. Okay, which is equal to, so now for this particular equation, so you know from ideal gas equation, PV is equal to mu RT. Okay, so from this I'm taking P to this side, so and then V to that side. So instead of P by T in this equation, replace it by mu R by V. So ds is equal to, instead of delta dq by T, I have written as ds. So this is mu Cv delta T by T plus, instead of P by T, I am writing it as mu R by R, mu R into, you can write it as delta V by V. Okay, so next I am going to apply the limits. Next I am going to apply the integration and also the limits. I am going to substitute the integration and also with the limits. Okay, so this ds, so you know the limits, initial entropy to final entropy, so which is equal to, so what is the limit? So you know that, so here we have a change of temperature, so the temperature limit is T1 to T2. So this mu Cv are constants, so the limit is T1 to T2 delta T by T. Okay, so next plus, so here mu R as constants. So here we have change of volume. So here we have the volume limit as V1 and V2. So V1 to V2 delta V by V. Okay, so this is can be written as delta S, you know already. This is a totally written as delta S. So here this mu Cv, so delta T by T, when you integrate, you will be, it is log E of T for the limits T1 to T2. Similarly, here we have mu of log E of V or the limits V1 to V2. So delta S could be written as mu CV. So from the logarithmic formula, you can write it as T2 by T1 plus mu R log E of V2 by V1. So this is the general equation to represent the change in entropy with respect to CV and R. Okay, see, mu CV log of T2 by T1 plus mu R log of V2 by V1. So first we have substituted delta Q is equal to delta U plus delta W, you know that. So the heat content with respect to internal energy is mu CV delta T for work done P delta V. Now I divided all the values by T. So you know the change of entropy as integral of dq by T when the temperature varies. So this is ds, which is equal to mu CV delta T by T plus mu R delta V by V. So when you substitute the limits, you will be getting this equation. Okay, next, according to this PV is equal to mu RT, from this gas equation, we are getting another equation, that is P1 V1 by T1, which is equal to P2 V2 by T2. So from this, I am going to write T2 by T1 from this equation, T2 by T1 as P2 by P1 into V2 by V1. Okay, so now I'm going to substitute this value for, I'm going to replace T2 by T1 by this particular equation. Okay, let us see what happens. Okay, so you know this equation. So delta S, you know that, which is equal to mu CV log E. So instead of T2 by T1, I'm going to replace it by P2 by P1 into V2 by V1. So P2 by P1 into V2 by V1 plus mu or log E of V2 by V1. Okay, so now see that I'm going to separate this equation. So mu CV log E of P2 by P1 plus mu CV log E of V2 by V1 plus mu R log E of V2 by V1. So see that, so this equation could be written as it is. See here mu log E V2 by V1 is common for these two equations. So mu log E of V2 by V1. So here we have CV plus R. So you know this equation. So Cp minus Cv is equal to R. So from this, Cp will be equal to Cv plus R. Okay. So now replace Cv plus R by Cp. So this equation will be, so delta S will be equal to mu Cv log E of P2 by P1 plus mu Cp log E of V2 by V1. Okay. This is also one form of the general form of the equation. Okay. General form of equation. I think I have replaced T2 by T1 by this product, pressure and volume product here. So these are separated into two equations. So you know that Cp is equal to Cv plus R. So I just replaced it. I have got another equation. Okay. This is the general form of equation. Now we will see the change of entropy for different individual process. Okay, we will see the entropy, change of entropy for isothermal process. Okay, so you know that from first law of thermodynamics, delta Q is equal to delta U plus delta W. Okay, so delta Q is equal to, for this value could be written as CV delta T, so plus P into delta V. So you know the entropy is nothing but integration of dq by T. So now substitute for this dq, substitute these both values. So it could be written as integration of mu CV delta T by T plus integration of P delta V by T. Okay, so now you see that what is isothermal process? Isothermal process in which temperature is equal to constant. Temperature is equal to constant. So this term becomes 0 because there is no change of temperature. So this term becomes 0. The remaining term is this one. Okay, so delta S is equal to integration of P delta V by T. So from from ideal gas equation PV is equal to mu RT. Okay, so just writing. So from this P by T could be written as mu R by V. So replace P by T by mu R by V. So this could be written as integral of P by T could be replaced by mu R delta V by V. So when you apply the limits, so mu R V1 V2 delta V by V, so which is equal to delta S is equal to mu R log E of V2 by V1. So this is the change of entropy value for isothermal process. Mu R log E of V2 by V1. This is the change of entropy value for isothermal process. Okay. So now we will see the change of entropy value for isochoric process. So next we are going to see for an isochoric process. So isochoric process, we know that volume is equal to constant. Okay, so from first law of thermodynamics, delta Q is equal to delta U plus delta W. So you know that as volume is constant, the work done will be 0. So you know that delta Q will be equal to, so this is can be written as delta Q is equal to mu CV delta T. So this change of entropy will be integral of dq by T is equal to integral of substitute this value. So mu CV delta T by T. So delta S. Apply the limits. So mu CV is constant. So when you apply the limits T1 to T2 delta T by T. So this equation could be written as mu CV log E of T2 by T1. So delta S is equal to mu CV log E of T2 by T1. This is the value for isochoric process. Okay. So we have a process called as, so I could write it here. We have adiabatic process. So in case of adiabatic process, you know that delta Q is equal to 0. There is no transfer of heat and there is no heat going inside or heat coming outside. So delta Q becomes 0. If delta Q is 0, you know that delta S is equal to delta Q by T. So in which delta Q is 0. So automatically we can say that delta S is equal to 0 in case of your adiabatic process. In case of adiabatic process, delta S is equal to 0. Okay. So at last we have isobaric process in which pressure is equal to constant. Pressure is equal to constant. So you know that in case of this pressure is equal to constant, the heat supplied, the change in heat will be written as mu Cp delta T. Mu Cp delta T. So what is the change of entropy? Is equal to integral of dq by T, which is integral of mu Cp delta T. So mu Cp is taken as common. So integral of apply the limits T1, T2 delta T. So I forgot the T value. Divide by T. Okay, so delta S is equal to mu Cp as common. When you apply the limits log E of T2 by T1. Okay, so integral here I apply the limits. So mu Cp log E of T2 by T1. Okay. written very small. T2, this is T1. Okay, so this is the value for isobaric process. So we have discussed about the change of entropy for a different process, and we also discussed the general equation for a gas in this video. Okay, thank you.